and the other people are just collaborators that we have in other places, like, well, the more relevant is Marcus Büttiger, who is one of the first person that studied these mesoscopic systems, and the rest are Rafael Sanchez, Monique. These are postdocs. Minchugi is a professor in Korea, and Thierry Martin is also a professor in the University of Marseille. So then I wanted to motivate why we study, why we make some research on these systems, and then, well, I prepared a previous, another slide just to motivate, but then at the very last time, then I decided to eliminate, but I did a very short motivation here. So why we need to study these systems that benefit very much from quantum mechanics. These are very small systems, as I show you later. And now, our motivation is because the modern technology that we use currently, every day, is based on some fundamentals of quantum mechanics. So we use lasers, transistor, magnetic memories, or magnetic nuclear magnetic resonance. So we are using every day this kind of devices based on quantum mechanics rules. So we are in these days we are in a kind of a technological revolution, which is based on quantum mechanics rules. So then the new technologies require more and more tiny objects, as we will see in the next transparency, and even we can design new materials, engineers a la carta. I mean, we can just say we need a material with these properties, and then I can try to look for these properties in a material that I can do by myself by hand with this with components that have very small dimensions, as we see now. So what I want to show you is, well, the first is the mesoscopic systems, the physical scenario in which I'm going to move. Then how I characterize these systems, the type of measurement that we want to address in these systems, and some specific examples. Okay, when I arrive to this part, then I will be more specific and not so general. But it's okay. So. The system that we are interested in are these tiny objects that with sizes that typically go from 1 nanometer, that is of the order of the atomic scale, atomic or molecule scale, to several hundreds of nanometers. Okay. So at this scale, we need to use quantum mechanics. These are nanosystems because this and this. These are nanosystems, the system that which have these sizes, and we can see that not only we can describe the, let's say, natural world here in this range of sizes, but also we are developing artificial devices that are that belong to this nano scale. Okay, so here we have, maybe you don't see, but it's nano transistor, nanoparticle, quantum dot, and atom. So then, as I said, the new technologies especially the modern microelectronics, needs to integrate many transistors in a very small area to form a chip. So then, once again, probably many of you have already seen this plot, we have already arrived to the nanoscale here. So each 2 or 3 years, we have to check again these lines for the forecast for the size of the transistors, and we are now arriving to very small transistors. So this is just an example. So then, of course, we need some description of these systems in terms of quantum mechanics. For instance, in this unit of basic unit of an integrating circuit, that is a transistor, which means something like transfer and resistor, we have problems at this scale, at the nanoscale, because we can have some tunneling effects between the two electrodes, the source and drain, because they are communicated here by this channel. So then there is a problem now that only quantum mechanics can solve, and it's because we can have some tunneling between the gates and the channel, okay, the electrons. So then we need to consider quantum effects. So here it's just an example, a nice picture in which there are 150 million of transistors integrated. So then in quantum mechanics we need to deal with the new effects that are not present in our microscopic world, and this is, for instance, the tunnel effect. So we can have tunneling. In the classical work, if we want to overcome a barrier here, if we don't have enough energy, we cannot do that. Okay. However, in quantum mechanics, because of the wave nature of the particles, of the carriers, then we can transmit particles from one side to another side, even if we don't have enough energy to overcome this barrier. So this is the usual tunneling effect, and then this gives you many different physical phenomena in these small systems. Like I will tell you later. So then, not only the tunneling effect is important, but also quantum mechanics offers the possibility to create superposition of states, and these are the usual way to describe a quantum mechanical system. And then with this we can use to perform some quantum information or quantum computing implementation for the new technologies. We can use the spin, which is an intrinsic characteristic of a quantum system. So we can, even now there are some devices that employ the spin degree of freedom of the carriers to build hard memories and hard disk memories and these kind of things. And we can even also use the detection and generation of single photons, okay, which can be seen as quantum emitters in the field of optoelectronics. So then which basic physical phenomena I have to take into account in these systems. The first one is that I have systems now in which the quantization of the electronic density of states is already present. I mean, in this system we have quantization of the energy levels. And we can have also quantization of the conductance. This I will show you later. We need to take into account, since now the carriers are described by its wave nature, then we have quantum interference phenomena arising from the wave mechanical properties of the electron of the carriers in general. Tunneling and Coulomb blockade, I will show you later. We can have also mesoscopic vibrons, because we can use some mechanical properties of these systems, and mechanical motion induced in these systems is done in quantum of vibrons, which is called vibrons. Then we use also the spin degree of freedom. So then we have to have present that we are dealing with these kind of effects. Okay. So then, not only I'm interested in tiny systems, because these belong to the quantum, let's say, quantum world, but also I'm interested in particular in mesoscopic system. Majority mesoscopic system belong to the set of very tiny systems, or very small systems, or nanoscale systems. But you can have some mesoscopic effect even in macroscopic system, because what is needed to have a mesoscopic system is just the only requirement is to have some phase coherence. So one can think about a superconductor as a microscopic mesoscopic system, because it maintains its coherence. So mesoscopic is something that is in between. Because of this, they call mesos. So it's it's neither macro or nor nano. It's something that is diffusive between these two words. So then the definition is that we have systems with a size that is much larger than the coherent length. This allows to us to have interference. So then we can build systems in which the wave nature of the carriers is manifested in their properties. And then the typical system that we are used to describe are, for instance, closed rings, and the mesoscopic effect is to have some persistent currents, as I will show you. For instance, we can have Haranoff-Bond interferometers when we have some system in which we apply a magnetic field to induce some interference between a path in which you have a potential vector coming from the magnetic field and a path in which this is not present. Then you have conductance oscillations. Chaotic cavities are another example of mesoscopic system, because here you have some universal fluctuation of the conductance because of the weak localization. This means that the electrons can interfere with itself, and this gives you some funny characteristics in the transport properties of these systems. Then also you can have quantum dots, which are the so-called artificial atoms, quantum point contacts that are constrictions in nanosystems, and quantum capacitors. Okay. So I will describe some physics of quantum capacitors and also on quantum dots. More introduction, just to show you the wave nature of the mesoscopic system is better. I mean, we can find a very good example here. This is a surface of copper atoms, formed by copper atoms. It's a surface of copper atoms, and then we have ions on top of this surface. And with a scanning tunneling microscope, we are able to move the iron atoms in this way, just forming this cycle. So the interference between the wave, the electron waves, then give you this nice pattern here, like this circular that are here. Okay. So then you can see, using this scanning tunneling microscope, you can see directly the interference between the electrons. So then, since now we have introduced the type of system which we are interested in, now we need to say what we want to measure. So then we want to measure transport properties, which means that we want to say, okay, I send here some electrons, and then I want to see how many electrons, or the current that I have, when there is some scattering center here. And the nice thing is that with this very basic example of it's just a one channel calculation here, we just consider a one-dimensional problem, then we see that the current is proportional to the density of states in this one-dimensional channel. That can be written at the end as this expression. So then we are interested in see how is the current when you transverse this barrier, and the response, the answer is just the transmission through this barrier times the voltage that I applied to get some current, of course. And then if now I divide I between EB, because this is a linear response calculation, this is a linear response calculation. I mean, I apply a very small bias. Then I get what is called conductance. So then the conductance is given by actually the transmission. So then what I measure is the transmission through these systems. And E squared over H is the unit of a quantum conductance, or when I don't take into account the spin. Okay, with the spin, then I have a factor 2 here. So then I'm interested in conductance in transport measurements, but if our scatter is not just a variable that is very easy sample or basic sample, if I have something more complicated, then I can use what is called scattering matrix, which relates let's say the ingoing states with the outgoing states. So then this just transforms the input into an output. If I know the reflection and the transmission coefficients of this scatter, then I can know how is this S matrix, the scattering matrix, and then I can characterize completely the transport properties of my system. Okay. So it's important to realize that this scattering matrix has some important properties, like the current conservation, which is translated into a S matrix which is unitary. So then I will show you now that not only it's important to characterize this with a S matrix in this way, but also I can take into account that I can have many channels here, okay, that connect with other channels in the outgoing part here, and only if we account this into the reflection and transmission coefficients with these indices here that label the channels, then I can describe a problem, a transport problem with a scatter that allow to have many channels. So then, once I know what I want to measure, then I will give you 2 or 3 examples of mesoscopic systems. This is a quantum ring in which there is interference here because we apply a magnetic field, and then the conductance becomes an oscillatory function of the applied magnetic field. And this is very nicely illustrated here because you can see this oscillation of the linear conductance. This is the linear conductance versus the magnetic field. Okay, so this is an interference sample in a mesoscopic. This is an example of interference in a mesoscopic system. Another one is the conductance, the quantization of the conductance here, in which you see that if you take, for instance, a quantum wire in which you confine the carriers in the y direction, where in the x direction you have free propagation, then you end up with a wave function that accounts here the channels in which the channels obtained when you confine in the y direction here, and the propagating modes here. So then you see that each time that you send an electron into the wire, okay, and can access to one of these channels, then you get a step here. So these steps are just the translation of these discretized energy levels here. Okay? That are the channels. So then the conductor presents this quantization and can be described as the transmission of each of these channels, okay? Like this. So this is a generalization of the previous transparency. So I can escape from this. I think this is just an example of what is called persistent current, and now you have a ring which is penetrated by the magnetic field, and this is a normal ring. What is important is that here this is a normal ring, and you can get a persistent current in the same way as you have when you consider 2 superconductors, okay, with some phase difference. You can establish a Josephson current that is this phase units. So then this is only when you have a superconductor you can get this dissipationless Josephson current. However, here we are considering a normal ring, so this is normal. And because because here you are considered a system where the carriers have some phase coherence, then the current through this ring must be continuous, and then by applying these conditions, then you can get a current that is called persistent current, that is dissipationless. The only way to detect this is through the magnetic moment, and this was already measured in 2009, one of the first measurements of these persistent currents. But what is important, that is a mesoscopic effect that can be only present in metallic rings. So
I don't understand the inequalities. I don't understand the role of the inelastic length. Elastic means that there are collisions.
Well, yes, I mean it's just to avoid some decoherence in the system.
Yeah, but if you have collisions, can you have a coherence length larger than this?
Well, this can destroy this persistent current, but it's not. But you can still have some inelastic scattering in your ring, and at the end you can see this persistent current. I mean, not if you have many scatters in the ring, then you destroy this resistant current. But a small amount of scatters can be present, but always you need to require to have some phase coherence in the system. Okay. I don't know, maybe I don't understand.
Question, I mean, because she's saying simply that the size of the ring is smaller than the inelastic length, the finished story. Then you have kind of ballistic transport, and there is no inelastic collision. I mean, there are forces on the border, but they don't. There is no inelastic collision between electrons. So this is what she put the condition. Currently with L smaller than inelastic.
Yes, you need to maintain the phase
my point
coherence.
is that inelastic is usually that you lose some energy. And I don't see how can you maintain something which is losing energy but without injecting energy. But probably what happens is that the equations are not really inelastic. There should some interference and compensate the phase. This is probably what
yes, I mean, you can allow some inelastic process, but in a way that you don't destroy completely the coherence. In this sense, you can still have this persistent current. Probably this make a smaller the persistent current. If you introduce more and more and more, at the end you destroy this. But this is a very small current. It's only of the order of 1 nanoampere. Well, I think that I go directly to the quantum capacitor, which is the system that I study. I will present you 3 types of samples that we have studied some mesoscopic physics. The first one is the quantum capacitor, and this was studied in 2 different works. The first one was just considering the electron-electron interaction in a mean field level, and the second one was just to account for many body interaction. So first, what is a RC circuit? When you have a resistor in series with a capacitor and you apply a DC voltage, okay, then the charge of the charge is stored in the capacitor in this way, okay, until it reaches the total charge that can induce, that allow to have this voltage drop that you apply with the battery. Okay, so then you apply, you have your battery that give you this B voltage drop, and then discharge the capacitor with time in this way. Okay, so then for times much longer than the RC time, then you get the Q naught. That is the charge necessary to allow to have this voltage drop along the classical capacitor. So then this RC time is the charging time for the capacitor. And now if you have some alternative current here, you charge continuously the capacitor. But if you are interested in well, this is somehow the inverse of the impedance. This is the AC conductance, that is the ratio between the AC current divided by the AC signal for the voltage. Then you get this expression when you make an expansion at low frequencies. So then this is important because here there are 2 parameters that appear. One is the capacitance of this classical circuit, and then you have the resistance of this RC circuit. But this is classical. Now, what happens when you account for coherence and when you introduce some coherence effect? Now, we need to distinguish 2 cases. One case is the previous one, the classic, when the interaction dominates with respect to the kinetic energy. Here the kinetic energy is just given by the mean level spacing of your capacitor. So then, in this case, the good description is the previous one. However, in the opposite case, when the RC time is much longer than the D-wheel time, that is related with the mean level spacing, then we need to include some quantum effects. So then now we are dealing with this case. How we can proceed? Well, we can use the previous scattering theory with the scattering matrix generalized to account for a problem where you have some time dependence voltages, and the conductance, the external conductance, is given by this expression. So here is the Fermi function of your quantum capacitor. The quantum capacitor is just given by this region that is a kind of big dot. On top of the big dot you have a gate, and here is the reservoir, okay? And here you have a constriction. So now you can calculate what is the AC conductance in response to an AC signal applied to the reservoir. Okay. And the AC conductance is given by the scattering matrix, but evaluated at the energy E plus H omega, which H omega is something that has to do with the Fourier transform of the AC signal, the Fourier transform in frequency of the AC signal in time. So then the AC conductance is given by this expression that is characterized by the S matrix. This is the only thing that we need to learn. If we have our S matrix, we are able to calculate the AC conductance. And in the S matrix, we have all the mesoscopic phenomena or the interference and electron. So now we include some electron-electron interaction in a very crude model. So we just say that, okay, if we just introduce some charge in the dot, then the internal potential reacts. So then we can use a discretized version of the Poisson equation with the applied voltages V1 and V2. Here, V1 and V2 is the generalization when you have two reservoirs, V1 and V2. Quantum capacitor with two reservoirs, okay? So then the only thing that is important is that here we include some internal potential with some response that is given by this pi function. But then we require to have gauge invariance in the theory, which means that if I just shift all the potential to the same quantity, then the current cannot be different. So then this means that this AC conductance must be equal to this pi function. And including this here, and calculating the ratio between this current and the AC signal, then I get some expression, which is given by this expression. But it's important to realize that here we are included all the scattering matrices that describe our quantum physics. If we continue further and we make the expansion in low frequency, we recover exactly the same expression as in the classical system. The only difference, which is the quantum difference, is that now these two parameters, C mu and RQ, are quantum. Now, what is interesting is that is to realize that this C mu has two different terms. One is coming from the classical world, the classical capacitance, and the other one is related with N. and n is just the density of the state of our big dot or quantum capacitor. Okay, this. We can think about this like a big dot with some quantized levels. Okay, so then the density of a state of this big dot is included here in the what is called electrochemical capacitance. So then this electrochemical capacitance has into account the classical and the quantum effects. And the what is named charge realization resistance is given by this ratio between this n, where at the end n is the density of a state, but it's related with the scattering matrix. So if one make the calculation, at the end one realize that actually this RQ is quantized. So independently, what is important is that it's quantized independently on the transmission through this quantum point contact, through this channel. So you can have a very large transmission or a small transmission that this RQ is quantized, because this is related with the coherence of your system. As long as your system is coherent, then you will have a charge realization resistance quantized. Okay. So experimentally, this can be seen. Okay, they measure the imaginary and the imaginary part of the AC conductor and the real part of the AC conductor. And in this plot, they show that this is a very complicated way to plot, at least for me, the result. This is a kind of Nisquith diagram, but this blue curve shows that the charge realization resistance in a quantum capacitor is quantized, has the value of h/2 e squared. And this value, the factor 2, is nothing to do with the spin. It's because we are considering just one reservoir, one channel. So if you have electrons with spins, then you will need to add an additional factor 2 here. So then you get h/4 e squared. So then the comparison between the two systems is just classical system I have this, quantum system I have this, with quantum corrections included in the capacitance, because I need to include some quantum capacitance that is proportional to the density of the state of my quantum capacitor, and RQ that is given by the quantized value given by this. Okay. But this requires to have a complete coherence across the entire system. Now you can include some Coulomb blockade effects, and this is what we did here in this work. The Coulomb blockade means that now in our capacitor, if we want to put an additional charge, okay, then we need to pay an extra energy that is this charging energy. This is similar to the internal potential that we talked before, but here, when you are in the Coulomb blockade regime, unless you provide to the system this energy, then the transport is blockade. This is related with the oscillation in the conductance as a function of the gate, because you get some peaks in which the charge fluctuates, okay, and in which the charge is blockade here. Okay, so then this is the so-called Coulomb blockade effect, and to include this in the theory, we need to deal with green functions. So before we used scattering matrix, now the scattering matrix cannot allow to us to include some interesting effects due to the interaction. We can just implement some crude model of the interaction through the discretized version of the Poisson equation. Now we just use the green functions and to characterize the system and include in the self-energy some Coulomb interaction through this kind of self-energies. And here we employ again the previous theory by constructing the S-matrix through these green functions. The previous one was just a scattering theory without including itself the interacting effects. Here we include the interacting effect in the scattering matrix through the green functions. But the rest is the same. We need to calculate the AC conductance, and then we were able to prove that even in the presence of quantum effect, Coulomb interaction, this charge relaxation resistance is still quantized. So the quantization is not destroyed by the Coulomb interaction in this respect. So then I will escape from these 3 transparencies that include the magnetic field, because they are too specific. And the next thing that we do is to include many-body interactions. So then we need to include some correlations between the capacitor and the contacts. And these correlations are usually accounted for the Conduct effect. So then now I use the Conduct effect in the sense that now the reservoirs can allow to our quantum dot to flip the spin in this so this spin just go here, then the 2 spins are in a virtual state because they don't have enough energy to be transported through the quantum dot, and then at the end I just go out with the opposite spin that I was in the initial state. Okay, so then with this mechanism that is done through these virtual states, I can build a correlate state between the electrons in the reservoirs and the electrons in the dot, the localized electrons and the delocalized electrons. At the end, this kind of interaction is translated in an antiferromagnetic interaction between these electrons and these electrons, which is called the Kondo coupling. So then we need to include in the previous model some Kondo physics in this description. So then we calculate again RQ and CQ through the charge susceptibilities, and these are calculated using some very complicated numerical method that is called energy. Okay. So then we show that even in the presence of correlation between the electrons in the contacts with electrons inside the quantum dot or the big dot, we still have some quantization of the resistance. And what is important is that in the previous description of the Coulomb blockade and when we were using the Poisson equation, in the previous cases we relate the quantum capacitance with the density of states. However, here when you have many body interactions, this is no longer true, because the quantum capacitance in this region, which is a region in which the charge does not fluctuate, okay, but you have a very high transmission, this region, this is the gate of the dot, then the quantum capacitance is very small. So then this means that, okay, for a mean field study, I can interpret the quantum capacitance with some kind of density of state, but when I include many body interaction, this is no longer true, and the interpretation is more complicated. This is the final message of this. And finally, we study also this quantization of RQ, but at finite frequency, and we found two peaks that depart from the quantization of this RQ at zero frequency. At zero frequency is quantized. When I move to energies of the order of the characteristic energy of this Kondo effect, then I get some deviation, a very large RQ, and this is because of this. Of this diagram here, because when I provide some energy to the system, then I have some particle Hall excitation that introduce some decoherence in our system. So I have just 10 minutes, and then I can maybe escape from this. Actually, I prepared many. As usual, I usually do this. So then I can just tell you what is this nonlinear fluctuation relations that is related also with the third example of this talk, and this was a study in these two works, and this is related with the following. With the previous studies, we just used conductances all the time. So then this was related with the mean average of the current. Now I want to go further and to study the complete full quantum statistic of the charge transfer. So then I can ask myself what is the distribution of n events when I measure in a period of time t naught these events. So then I can count events like trains arriving to a station, of the occurrence of zeros in a roulette game, or the number of electrons in an electric current. So then I can characterize my distribution of the charge transfer in a time t by some distribution. Okay, I can have this or this or this, and this gives me the complete information of the system. I'm not only focused on the mean value, because the mean value is just the average of the current, but also I want to access to the variance, which is the so-called noise, in the short noise in the transport theories, or even I want to calculate the squareness of the distribution of the four cumulants. Okay, so then I'm interested in calculating all these cumulants of the charge transfer distribution. So then I want to do that, and I can build this P function, and then I can even make its Fourier transformation with this variable that is called Quantum field. Okay, then I have access to the cumulant generating function, and just by derivating with respect to the Quantum fields this cumulant generating function, I get all the cumulants of my distribution of the charge transfer. I can even include two Quantum fields to count charge in different contacts, etc., and measure correlations. So then this is what I can do. Now I can expand the current in terms of voltages, and then I get this G1 and G2. And then I can expand also, for instance, here the noise in terms of the noise at equilibrium and the noise susceptibility. I know that if I use the Kubo formula, then I have a relationship between these two coefficients. But I don't know what happened out of equilibrium. So this S and A, we can just omit them. This was just a mistake. So then I don't know if there is out of equilibrium relationship between S1 and G2 and the other ones that are not written here, but you have more and more cumulants. So then there are two works on this. One is by Heidi Foster and Marcus Buttiker, in which they use this relationship that is the fluctuation dissipation theory of the equilibrium, okay, which is given by this. And I'm not an expert on this, but the only requirement is that you need to make micro-reversibility or local detail balance. Okay. There are people that have already used this, but in presence of magnetic field. And in presence of magnetic field, you break micro-reversibility, and then this is, you are not allowed to do that. Okay. So then the problem is that if you want to make this relationship between the previous coefficients, then you get different results if you use micro-reversibility in the presence of a magnetic field, or you don't use this. You can use another relations specified in this work, okay, but it's not micro-reversibility. And you get different results. For the moment, the experiments cannot distinguish between them, okay. But there are some experiments in which they have measured this quantity and this quantity. These are just this previous coefficient, the noise susceptibility and the second derivative of the conductance with respect to the bias. And this phi function means that they are evaluated at B, a magnetic field B and minus B. And this is the third cumulant. Okay. So one of the theories relate the three of them with a single relation, and the other theory, this one, relate this coefficient with this and this coefficient with this. Okay. So then the experiment, I just jumped the experiment, but we studied this in the absence of detail balance in a double dot system. And our double dot system was an upper dot here and the lower dot here that are connected with a capacitance. So then we were able to drag current through the upper dot just by inducing a current through the dry dot. Okay? And then this is the drag current that we obtain by just having V1 equal to V2. These are the bias drop at the contacts. So here we just put one dot at equilibrium and the other one was out of equilibrium. So due to the out of equilibrium fluctuations of the dry dot, we were able to induce a drag current in the upper dot. But what is important is that if we just focus on the upper dot and we look at the local detail balance, we see that the transition from the charge state 0 or 2 is different to one initial state to another final state is different if we reverse these two. So then local detail balance is broken in this respect, and we check if even if we break this kind of micro-reversibility, this system, the double dot coupled with this capacitance, with considering 4 charge states, 0, up, down, state, up dot charge, down, lower dot charge, or the double occupancy for the whole system. We consider in a master equation description this system, we were able to check all the fluctuation, nonlinear fluctuation relation in this multi-terminal device, where here we have the noises and the conductances, and these alphas are just labeling the different contacts. Okay? So if you write down all the nonlinear fluctuation relation for this particular system, you arrive to this and to this. And now we check this, and we had a perfect agreement in which we check here the noises, which was in one part of the equality, and the conductances. And we see that the black curve is exactly the same as the purple curve, and the same for different cases. So then, even in the case of broken local detail balance, we have this nonlinear fluctuation analysis, and then the last. So then I have shown here. I have shown the importance to deal with quantum effects to design new device as mesoscopic device, and I give 2 examples because I state the samples in the middle: quantum capacitors and nonlinear fluctuation relations. So, well, thank you.
Maybe ask, in the last, you talk about this micro-instability. So I understand when you talk about magnetic field.
Yes.
But here, when you have 2 quantum dots, I mean, what there is
well, the only, I mean, we call, we say that in the absence of local detail balance, we can have these nonlinear fluctuation relations, where the fluctuation dissipation theorem out of equilibrium was formulated when you have local detail balance. Okay, so yes, with the magnetic field we break.
Because time invariant is broken when you have magnetic field, and everything clear. But here I don't see that.
Well, it's because it's difficult to have a direct relation between them. We say this, you can see this kind of absence of that you don't have the forward and the backward movies the same. Okay, when I say that, when I say that when you go from the state 0 to 2, it's different if I reverse. Okay, this is in a way to say that you break local detail balance, and to some extent can be related with the micro-reversibility, but formally you don't break any time symmetry. It's just to say that the transition from the initial to the final state is different. I reverse the direction of the arrow.
I miss in this last part the non-linear fluctuation representation frames. I miss the quantum part. When, for example, in everything is quantum. When you have a semiconductor, you have the bands, and this is quantum. But in this talk, you are talking about a different kind of quantum. You are talking about the importance of having some coherence.
Yes.
In the formulas, so this effect is really a quantum effect in the sense of coherence, or is quantum because you have channels?
Well, here is quantum because you have some tunneling, etc. Okay, but it's not really in this particular case that we have studied here. It's not coherent. So this is sequential tunneling, and it's not coherent. But we have a further study of this in which we implement coherence to see if this is still valid, and it is. But I think that in this case it's much illustrative, this example with the kind of master equation, etc., that you can see how the charges are transported through the system. But if you allow to have some quantum coherence, then you can still have this fluctuation, this nonlinear fluctuation relations. So, but it is not. But it's more related with this out of equilibrium fluctuation dissipation related than to the coherence. Yes.
Any other question?